Hello everybody and welcome back to From Rhythm to Algorithm Part 4, the Incompleteness Theorems. Gödel's Incompleteness Theorems. It's been a while since I made a formal math video, but again it takes me some time to figure out the implications of what I've done. So we're just going to review his two incompleteness theorems and demonstrate what we've already demonstrated. What I've done is remember we talked about spelling a word constructs a variable. What I've done is taken the breadth of language and proven that the first, it is what it is the basis of logic. How does that relate to Gödel's incompleteness theorems? My research validates the first and expands the implications of sets, categories, and limits. And my research disproves the second incompleteness theorem. So what I'm going to do is just read through the Wikipedia article. This is just type in Gödel's incompleteness theorems. And I'm just going to read I've read the whole article, but I'm just going to read the first 3 paragraphs and respond to the verbiage of the language that makes sense to me. Gödel's incompleteness theorems are 2 theorems of mathematical logic that demonstrate the inherent limitations of every formal axiomatic system capable of modeling basic arithmetic. These models, published by Gödel in 1931, are important in both mathematical logic and philosophy of mathematics. The theorems are widely, but not universally interpreted as showing that Hilbert's program to find a complete and consistent set of axioms for all mathematics is impossible. The first incompleteness theorem states that no consistent system of axioms whose theorems can be listed by an effective procedure, that is an algorithm, is capable of proving all truths about arithmetic of natural numbers. For any such consistent formal system, there will always be statements about natural numbers that are true, but that are unprovable within the system. The second incompleteness theorem, an extension of the first, shows that system cannot demonstrate its own consistency. Employing a diagonal argument, Gödel's incompleteness theorems were the first of several closely related theorems on the limitations of formal systems. They were followed by Tarski's undefinability theorem on the formal undefinability of truth. Church's proof that Hilbert's something problem is unsolvable. And Turing's theorem that there is no algorithm to solve the halting problem. I'm not familiar with the undefinability theorem or the halting problem, or the Scheindung's problem is. So I'm not going to talk about that. But I have demonstrated that language is consistent and language swallows up all of mathematics very rigorously. More rigorously than has ever existed in a known mathematical proof. You have to read my actual thesis, it's on my website. But type in the word speciality. S-P-E-C-I-A-L-I-T-Y. And speciality, and I have done all of these things from linguistics to evolutionary biology to literally direct slang language, formal physics, and formal mathematics. And so what I've done is demonstrated all of known physics and then constructed, remember we talked about spelling a word constructs a variable. Speciality has 0 hits on Google. There's no definition for it. And so in the same way you have an identity in mathematics, if you derive a natural definition of a word, well, the sets, categories, and limits of what you've done becomes profoundly larger. Again, like I said, I don't know how many theorems I've proven, but we're talking proven sent to other people probably around 100,000. And so what I have done, the way that I demonstrated consistency is I demonstrated a new axiom. Speciality has no hits on Google, but speciality is the natural tendency of biological organisms to differentiate for sexual antagonism, right? Forget human beings, go look out in nature, there's plenty of sea creatures and animals that have fur coats that are intricate fur coats that are consistent with the geometric arguments that I presented to just attract a mate. And right, I just watched the other day on the National Geographic Channel, like sand crabs at the bottom of oceans forming these really intricate patterns just to either build art or just to attract a mate. Same thing with a bunch of little different types of birds. They build little pieces of art to attract mates. Same with peacocks and their form. And so in the human species, right, there's 0 hits for speciality, but it's 100% empirically evident every time someone says the word special. Speciality is just special with a suffix at the end, right? ITY. And so this the proof of speciality is literally going to have to be published as a book, but that is what we've done, is we've shown consistency from natural language to begin with, which again is the highest caliber of mathematical proof that could ever exist. Now to the first one, it expands the implications of what the theorem states. Let me read it again. Make sure my camera's still on. Cool beans. Where did it go? Sorry. Should have had it written down. But no, I don't know where it's at. But the other thing I wanted to say about what Kurt Gödel did himself was he basically assigned natural numbers to letters and said you can't, and then did a mathematical operation and said therefore these implications to language. Fuck no. That's what's incorrect. The theorem itself, the verbiage is correct, but the conclusion to say that you can't, whatever about the Hilbert's problem. The theorems are widely but not universally interpreted as showing that Hilbert's problem to find a complete and consistent set of axioms for all mathematics is impossible. And that is true. Because, now the same with the speciality, you've just watched me derive mathematics for very close to a decade continuously, and I can write like one more sentence. A fucking sentence. So now you get into the right, there's completeness, and I'm personally, believe it or not, I'm personally not that aware of like what you mean by hard problems or complete sets, but what the implications that it shows is, fuck, I just lost what I was gonna say. Come on, do math, Brad. Go do math. I'm gonna pause the video. I'll be right back. Okay, I'm back. I'm just gonna reread the first incompleteness. The first incompleteness theorem states that no consistent system of axioms whose theorems can be listed by an effective procedure, that is, an algorithm, is capable of proving all truths about the arithmetic of natural numbers. So we proved that a consistent system of axioms does exist, but is capable of proving all truths about the arithmetic of natural numbers. That is correct. There will be infinitely many statements about numbers that we can't prove. There'll be infinitely many statements about sets we can't prove, or categories, and that was the limitation I was getting at. But in addition to that, there's the same implications for language. Again, we don't even know, we'll have open questions about like the cardinality of sets of languages, or sets of letters, or sets of syllables. So if this is your first if this is your first video of my math that you're watching, I've proven, so when you when you introduce a new mathematical proof, there's always the slang analog is there's always more question. It always raises more questions than it provides answers. That's the everyday awareness of Gödel's first incompleteness theorem. But what was that? Reading, and so when I've demonstrated this proof of speciality, I've demonstrated a lot of implications simply about the shapes of letters alone, which I've called geometric linguistics. And so the breadth of mathematics gets tremendously bigger for real. So it just bolsters and it makes this one, it validates it to the core of what Gödel was saying, but it expands the implications pretty tremendously, to the point where clearly I can't even talk about them all that well. Continuing on, for any such consistent formal system, there will always be statements about natural numbers that are true, but that are unprovable within the system. That's redundant, agreed. The second incompleteness theorem is an extension of the first, shows that the system cannot demonstrate its inconsistency. No. And that's the part that again, proof by empirical demonstration. So that's probably all I want to say here for now. Like I said, I've read, if you want to read this whole entire Wikipedia entry, it's not bad, but I want to go watch, there's a 60 Symbols popular YouTube channel video about Gödel's incompleteness theorem, probably in early 2017 or 2018, because again, I've sent all of these people this stuff in late 2016, early 2017. But it talks about how his one-to-one pairing of natural numbers to letters, and it's a good explanation of the theorems. But this is what my research does, and again, it is what it is. It's clearly the logical basis of mathematics. But proving and demonstrating the logical basis of mathematics doesn't say too much about the completeness of a set, but the consistency, it's definitely consistent. Thanks for watching part 4.